in improving availability, reliability of products processes throughout their life cycle. Concept, design, development, testing, manufacturing, launch, returns, and repairs. So he covers all the facets of RAMS, and we are very keen to hear from you, sir. Thank you for
Thank
joining.
you. Thank you. I hope you all can hear me clearly.
Sure, sir, and we can see your
Yeah.
presentation as well.
Yep. So this reliability assurance roadmap is based on my 25 years of experience in applying reliability theory in the product development, product maintenance, and declaring end of life or deciding the replacement of the system or product or a process. So I will cover in this topic, what do we do? How do we apply this whole reliability RAM or PHM from the starting phase, and how do it follows through the whole life cycle of the product or system or a process. So, and I have not listed all the minute details in this roadmap. Only I'm trying to highlight the main events or main activities that should happen whenever you are thinking about a system, a product, or a process, whether it is a RAM or whether it is a PHM also. So in general, I will say that 6 main strategy wise, you should be looking at from the activity, 6 main activities strategy wise. And the starting when you have the initial phase of a concept, then what do you look at, like reliability requirements, reliability predictions. And then when you are moving into the development phase, you look at the how do you implement this design for reliability? How do you make this system reliable enough? And then what do you do to bring a confidence that my system is reliable before you start the operation or you launch the product or put the system in operation? And once you have done this operational phase or launch phase of the product, so you go through the reliability performance, reliability investigations, change. But the most critical one is this lessons learned during that journey. And then you bring back to any new product or even the existing product if you are still trying to create more systems. And then I will go briefly about what are the main challenges that we see in these activities and some examples from the telecom, from the defense industry, from the consumer electronics industry where I have been working. So the initial stage is this reliability requirements. And in defense industry, you have a very clear target defined, like in the fighter planes or even the emergency services, air services or road services or whatever it is. So they define it very clearly that what availability they need for the mission critical purpose, what should be the reliability, what should be the lifetime of the equipment, how quickly it should be repaired if something goes wrong. And sometimes they give you environmental conditions, but what they don't give you is the profile. Like if the fighter plane is going on just for 2 minutes above 100 degrees Celsius temperature, or it will be 2 hours above 100 degrees Celsius when it is completing its mission. So those are the lot of challenges that we get. And then coming back to the challenges side, the biggest challenge becomes like, how is it optimal cost to produce just 2 units or 10 units? How, to what extent we can define these reliability aspects of this product? So different methods that we use depending on if it is a larger population or a smaller population. Plus sometimes you don't have a requirement well defined from the customer side, or you are creating your own product. So what I call it like internal requirements. And then as a reliability person, it's a responsibility to define those requirements. And I think the previous speakers have dealt very well. How do you define those requirements? But overall, it becomes like, do you see this reliability target, reliability requirements as an opportunity or as a risk? And that mindset brings us how much you can invest in making that product more reliable. Are you looking at the shorter gain or for the long-term gain? So this culture-wise in the business side, if it is a risk or it is opportunity, it makes a big difference. And that difference makes a here that what is the strength of the system you're defining and what is the expected stress or load on those products. And the distance between these two depends on perception, that is it a big opportunity for me to commercialize or monetize this opportunity, this product, this system, or is it just I have to meet the requirements? And some challenges becomes like just in a small example, like they ask 99% availability per month. So if I am producing 10 units, so I get around 72 hours MTTR, mean time to repair for that product. But if the customer is buying just 5 units, it means no failure should be allowed, because downtime is 36 hours only in a month. That makes very difficult analysis and focus on the design for reliability, depending on what quantity of the use of the system or product that we are developing. And this factor sometimes we do neglect, because some people say, you have already 99% availability of this system, and I just want one, I want 99%. So becomes a lot of conflict. So it's a lot of challenges that you try to sort it out or negotiate. So initial phase, we are still in initial phase. Some industry that don't define very clearly industrial initial phase or development phase, it can overlap between initial phase or development phase, depending on the company culture or the product development or system development process. But in general, this reliability prediction and reliability demonstration, this is the widely misunderstood area in the industry. Due to various reasons, there has been some team calling it there should not be any reliability prediction, because it's like a crystal ball where you are just giving a number without a proof, or we are not able to verify that. So normally for parts count method and parts stress methods for the hardware, one can use. There are various standards for that, how to do it. It's very useful if you are just doing evolutionary technology to develop a new product. And then other area that is growing very fast is the software component reliability, because in the software there you have embedded software, and then you have a system software, and then other analysis software. So there are so many components come into picture that will ultimately reflect on your reliability of the system or product. And then other way we do is we look into this simulation side. You can do Monte Carlo simulations depending on this predicted reliability. And then you can look into long term, whether it is if the target is within a month, I should have 99% availability. You should be able to simulate and tell to the designer, to the business, that which area or which component is weak. And then you do the changes. sometimes in the base stations, I had to do a lot of simulations there. We could improve the reliability of the base stations quite a lot by just improving a few components and putting some components in a standby and some K out of N situations, or in a series system or parallel system. Then comes this, once you have done the prediction, then challenges starts with this testing. How do you do the test? What confidence you can have? There are a lot of theory around it, but in reality, when you start to test, the product will be not ready completely. There'll be shortcomings. There'll be a lot of noise when you are starting to do this reliability test or demonstration to the customer. We had to do many demonstration to our customer in Vodafone, T-Mobile, or even the defense industry in NATO, that the product that I have developed is reliable enough, or it will give me only one failure in 1 year of time. So in challenges becomes to agree on this, which method to use as per the which standards you have to use. In the test side, you have to look at the challenges becomes like, currently the products that our system that we design are very highly reliable, or the design in reliability is very high. So you don't get any failure during the testing. So you use the accelerated live test, highly accelerated live test. So there are various methods you use, but you need a lot of theoretical background to apply to come closer to the predicted reliability. So yeah, some of the customers still think it is a crystal ball unless until you have shown them through the test that this is the reliability we have achieved. Then comes from the initial phase, or when you are coming into the development phase, there are many tools people use for designing reliability. But what I found was that this failure mode and effect analysis, or failure mode effects and criticality analysis, both these methods give a quite good enough understanding of the product, that what are the failure modes that are likely to happen. Can we remove those failure modes using the design itself? Or if the design limitations doesn't allow me to eliminate those failure modes, can we do testability analysis, where can we do the monitoring or built-in test for those failure modes? And defense industry has been very, very good. Even so, that has been quite good, well-established practice. But in the commercial industry, when I was doing one of the satellite receiver, you get so much data you can pull from the system, but the expense, the cost to analyze those data is huge. I mean, it's sometimes you can't believe even that how expensive it becomes to analyze those data, or to collect even those data. Those data are available, but the third party who support you to collect globally will become beyond your business benefit. So we need to optimize at that level. Challenges that happens, like from the design side, you cannot detect all the faults that the system can generate, or you have identified through this failure mode analysis. And most of the, since the availability requirements in the defense industry or in other commercial industry is very high. So what do you want? You want to know exactly which system to do, which part of the product to be repaired, which part of the system to be repaired. So that's where you use the concept of isolation. So normally fault detection, you look for the 95% of the different faults that can happen in this product, we should be able to detect. And then isolation side, you look at the at least 100% is the target. People say that I'm able to identify which part of the system has led to this type of problem. And the other challenge comes, like similar failure modes can be generated to the different system and the different parts of the same system. So you get the false alerts and false alarms also. So the sensors or the monitoring system that you use, they have their own shortcomings. They are normally below 4% to 5% for a, it's a quite industry. In the industry, they accept it up to 4% or below 4%. Yeah, so when we have done the development, done the product test, trial, you start the launch or operation of the product. Irrespective of whatever you have done, there is always chance that your stress has somehow overlapped the strength of the product and the failure likely to happen. So in industrial side, people when they have done the launch the product and started the operation, the team who has been working on the product moves away to the new product, new system, or new process. But recently, there has been quite a lot of discussion in the commercial side that even if the project has finished, you have delivered the product, a certain core skill set should be kept in the same project in the operational side. And what we do when you uh, launch the product, you bring back all failures, all returns, all points of concern that system has generated for thorough analysis. And normally when you bring it back, you'll find it around 20% have the genuine reason that why system has failed. And 80% is more on the human reliability side, because we are quite weak in modeling the human behavior, how they will use the system. It can be either due to lack of training, lack of understanding, or in the design itself, you have not thought about those various huge conditions. So my recommendation is to do thorough analysis in the beginning for any concern that is raised during the starting phase of the operation or launch of the product, and then act immediately on those root causes and implement the preventive actions for those root causes. So, and in that way, keep on improving the product. Challenges becomes, as I mentioned earlier, the resources. When you move from one product, you do the design, launch the product, it starts to work, and then you move the core skills in another area. That's where the negotiation happens between different teams, different management. And then another question comes like, when do you stop this activity? See, it's again, do you see the risk or do you see the opportunity in improving these failures or removing those failures? And then other aspects happens like when the product has been in operation for some time, some period of time. How do you measure those performance? So in the beginning, if it is a mass production, or if it is a quite high number of products that is going to be used from the beginning, the batch failure rate has been very useful to indicate the quality or reliability of that product that is going out in the field. And that batch, by the batch, I mean, either you can look into the production month or production country, or if you made any change in the product. So homogeneous, is it the homogeneous population or not? That information is lost many times when you're doing the data analysis. So I prefer to any product that you are going to use in daily life or in your system or going to monitor it, we should be able to identify from the failure data itself that Does it belong to the specific week of production, a specific week when it was produced, when it was sold, when it was put into operations? And then on the longer term, field failure rate. That in many companies, it's still a big incentive for the business. In Nokia, out of 5 performance metrics, like field failure rate was the one of those. In a Sky Broadcasting, that's also like incentive of the executives and all the employee depends on the failure rate, how often it has failed, and that is measured every year. And normally you monitor continuously. The challenge with the problem with the field failure rate is that it doesn't say about the product reliability at all. It gives some indication that what my warranty population is doing, or the product that I have collected the data, how it is doing in the field. It doesn't say how my design has been with the product. So that just to understand the difference between the batch failure rate and field failure rate, I just give an example. Like if you're going from point A to point B, which is 100 kilometer further, and if you're driving in 100 kilometer speed per hour, you will be reached within 1 hour. But your speed at the time of 20 minutes will not be 100 kilometer. You may be driving at a 20 kilometer, or maybe driving with the 70 kilometer. So this batch failure rate responds to that at that specific time, what is the status of this product, and then you can adjust your speed accordingly to come up to 100 kilometer per hour average speed. Then when it comes to the measuring the failure rate, I have seen in commercial industry there are around 10 to 12 different way you measure the failure rates of the product. Uh, some industry, they say, okay, 10 failure out of 100, 10% is the failure rate. Some industry say, okay, 10 out of 100, if all failed in only December, so it is not 10%, they calculate a different way. Then they get into, some industry have better information that I had sold only 2 units in January, or I put operation in March in so many units. So you look into the different levels of details, and you can come out different values of the failure rate for the same product. And that becomes a challenge, because when from the supplier side, you are agreeing a certain reliability for a product, and then from the user side, if you don't, both of us has not agreed that how will we measure it, it comes a lot of conflict, and we had to go to the court also for coming to the final conclusion. So this can be very sensitive. So it's always good to, from the requirement stage itself, get into how are we going to measure the performance if we are putting the performance as a criteria in the supplier side. And another challenge becomes the noise in the performance data. So if you give the data to somebody, you come at a failure rate, but when you start to know the story behind those data, you come to the very different failure rate calculations. So one should be very careful and must be aware of the background of the data. Then the last stage during the operations, your investigation side, and you make changes in the product, in the system, or in the process to improve it, and feedback to any new product that you are creating in the, which is in the development phase, or negotiating some other products or systems. And this, irrespective whether it is defense industry, telecom industry, or in electronics industry, this is the weakest point, in the sense that whenever you are doing a new product, you will see they'll be repeating the same mistakes many times. We had, like in Nokia, we had some components, or in a satellite receiver side, some components has been failing all the time, and it still fails all the time till someone really takes into account that a thorough reliability investigation is done and a thorough change is a managed change is implemented in the business side. Otherwise, human being are very tend to have this inertia that this is the way we have done the design and it has been working for the last 5-10 years, and they keep on doing the same way. So as a reliability person, you have to do a lot of negotiations, facilitation, and managing different aspects of a product. So this is the famous our PDCA cycle where you performance is happening, you monitor it, you improve it, you plan it, then perform. You plan that what you are going to do, and then you perform your analysis, then you monitor that is it working, and then you improve it, and then you keep on going. So this should continuously go on, and this feedback is the most critical item for making any system highly reliable, whatever is a railway system or defense system or any system. The challenges is in any industry, I have not seen yet a very good feedback loop. Like there is no department or no single point of person who coordinates all this feedback loop at the same time have a technical understanding to implement those changes. It happens piecemeal wise, and also the priorities and incentives drives this feedback loop also, like what is the priority in the business or in the industry. Is it creating a new product, making very shiny good products, creating a new technology, or is it improving the previous ones? And then incentives, how these are incentivize those people. So coming back from the, this is my last slide. So coming from, starting from the beginning, you start with the reliability requirements, and it is not just one event at one point of time that continues throughout the product development, but you initiate, your priority should be to start with the requirement side, and that may continue even when your product is during the operations, because you will learn a lot during that process, and that will feed back to your reliability requirement for any system, PHM or uh, RAMS system you're trying to analyze or trying to develop for any product. And then your reliability prediction also depends, either you can do the standard based or you can use the batch failure rate or field failure rate site analysis. And then sometimes in the requirement and prediction, even if you use the learnings to improve your requirements attributes and your prediction methodology and your demonstration methodology, and then you all feed back into your design for reliability side. So it's an all continuous process, and we need to have a systematic approach to the reliability. One has to look into from end to end point of view. Like it is not just at one point you can just close the reliability side. And then other thing that I find very important that it's a cross-functional. It's not just the reliability person who is responsible for the reliability. It's everyone involved in developing the product. Like in marketing side, when I was looking at the Sanofi medical devices, like what should be the reliability of those? So I had to get in touch with the marketing side, repair side, logistics side, like how much many returns we can accept. What is our facility, reverse logistic facility that we can collect from the field those equipment? How can we uh, to meet the regulatory requirement that you will have only 99.5% failure of this product. So there are a lot of financial side, business organizations, different disciplines involved to achieve the success in your RAMS program or reliability. And then ultimately it's the mindset. Are you looking at as a risk or looking at it as an opportunity? Once you look at the as an opportunity, then you get tremendous support to do very extensive reliability analysis and you make the product reliable. So in summary, for reliability assurance, start from the requirement, go to the prediction, do the design for reliability. When the product is launched, please do continue with the feedback loop. Thank you very much.
Thank you very much, sir, for your talk. It was very interesting, sir. And we are really very thankful for you to sparing out your time and